Hello, I am Giovanni Sardina,
I'm Ryan Moedano.
I'm Travis Baguette. Alex Linder.
Vanessa Sanchez.
Jaron Lynn, Ayman Kakuki, Hadim Muhammad.
and we are Team Fear, Fire Extinguishing Autonomous Robot. Fire is incredibly dangerous. Whether it's Samsung's newest cell phone or a simple holiday decoration, without constant monitoring, what is to stop something like that from causing major fire damage? But more specifically, what if someone were to leave a candle unattended in our very engineering building? And now Vanessa here will talk about the competition.
Hi everyone, I'm Vanessa and I'll be talking to you guys about our project. So the purpose of our project was to build a robot that can find and extinguish a lit candle in a defined area. It has to be autonomous and it can only use 100 milliliters of water. So here is our playing field. There are 2 rooms connected by a 90-foot hallway, and each room has an island desk in the middle, and all of this is located at the bottom floor of the engineering building. Now what makes these rooms challenging is that there are obstacles along the walls, making each navigation of the robot very difficult. So now we get a candle that is 3 to 6 inches tall, placed in an unknown location. This doesn't change. Each team gets 3 attempts to find this candle. However, there are decoys. If a decoy is hit or sprayed with water, that run is terminated. All right, I'll send it to Alex to talk to you guys about our design.
So we started our design process by measuring the course and the doorways. This allowed us to choose a size that would help us maneuver around the course with ease. With differential steering in mind, we designed our robot to be wider. So differential or skid steering is done by driving the left and the right side at various speeds in forward and reverse. So as you can see from the animation, to turn right, the 2 left wheels are rotating forward while the 2 right wheels are rotating backwards. We decided to design our robot with 4 motors. This allows us to have more power than the competition and for us to cover the long hallways in a short amount of time. So our chassis is designed out of lightweight yet strong 1/4-inch aluminum, and our robot stands at 8 inches tall by 16 inches wide. We designed our robot to have fully independent suspension so that we have traction at all times, and our suspension is adjustable, which allows us to configure it for multiple applications. And now Ryan will talk to you about hardware design.
This is a comprehensive block diagram of our hardware design. As you can see, we've broken it up into different modules that allowed us to work in parallel. The microcontroller and the main board is in the middle. The sensors are at the top and off to the sides. The water distribution is down to the bottom left, and the motor board is at the bottom. Now I'm going to talk about the motor board. For Fear, we created custom motor controller boards. Each motor board has 2 full H bridges, which amplify the 3.3 volt PWM signal from the microcontroller into a 15 volt PWM signal that can control the motors. There are 2 of these motor boards on board Fear that will allow us to control the speed and direction of each of the 4 motors. Now, some of you may know H-bridges tend to run a little hot, so we performed a rough thermal analysis of our design. The thermal area of the IC is about 1/10 of an inch by 1/3 of an inch, and this yielded a junction temperature of about 215 degrees Celsius, which is way beyond the max temperature of 150 degrees Celsius. So to fix this, we tripled the thermal area by adding a large ground plane with several vias underneath the IC where the thermal pad is, and this decreased the temperature to about 99 degrees Celsius. Although this is still very hot, it's within the operating temperatures of the IC, and for added measure, we included an aluminum heatsink to further decrease the temperature. Next is the main board. The main board serves as the central hub of our robot, and it's the brains. Our team decided to choose the most powerful microcontroller from Microchip for very specific reasons. We chose the PIC32MZ for its 100-pin output. This was to ensure that we had enough expansion capability for our hardware down the line, and we also wanted to have a fast processor speed to allow our code to run without any limitations. The MCU is responsible for sampling the output of the sensors via ADC, providing the PWM for the motors, And as well as that, we have 2 mission select push buttons on our board, which allows FEAR to react to very different scenarios throughout the competition. The first one is a mapping mode in which FEAR will navigate through the course, marking positions of obstacles and detecting the flame. And the second one is the solving mode, where it will travel to the flame using the course map and extinguish it in the fastest time possible. Next, I'm going to pass it off to Travis to talk about the sensors.
All right, thank you, Ryan. So for our robot, we're using a variety of sensors to collect data from the outside world. This is the sensor board we're using to aggregate all of those signals into a single place. We have headers for our ultrasonic rangefinders and our IR rangefinders. And for our flame detection unit, they are bare photodiodes. So we're using an op amp to amplify the signal given from those. Now overall, our robot has about a 270-degree cone of detection. And in order to achieve that, we're using 9 infrared rangefinders, 3 ultrasonic rangefinders, and 6 flame sensors. Now the first of the sensors I'm going to talk about are our infrared rangefinders. We used a rangefinder from Sharp. It's one of the best that they have on the market right now. It has 5 feet of detection and has a 60 hertz refresh rate. Now in the world of electronics, 60 hertz doesn't sound like a whole lot, but that's actually 3 times faster than the previous version and other competitors on the market. The reason we like this sensor, aside from its long detection range and its refresh rate, is also has a very narrow detection cone, which gives us pinpoint accuracy of what's directly in front of it. Now you can see 2 graphs here. The first one is the manufacturer's data sheet, and the second one is our own collected data. As you can see, ours is a little bit more linear than the manufacturer's, but it's still a very non-linear graph. Now what that means is when we're interpreting this data, we're going to need a lookup table to translate those analog voltages read into real-world distance measurements. Now the next of our sensors is an ultrasonic rangefinder. Now you might be asking yourself, why do we need an ultrasonic rangefinder if we already have an infrared rangefinder? Well, for one, its max sensing distance is about 20 feet, or 4 times longer than the infrared one. Also has a much wider cone of detection. So when we're looking in front of us, we can very easily find big planes like walls. And also one of the biggest things is, since we're using infrared flame detection sensors, our IR rangefinders will interfere with those. So at certain points in the course, we will need to turn off our IR rangefinders and only use ultrasonic to prevent that interference. Now for our flame detection, we're using a sort of spectrum analysis. That is because an open flame releases broadband radiation, whereas the decoys release a very narrow band of radiation. So we've selected 2 different sensors that have peak sensitivities at different wavelengths. So when we look at these sensors, we can decipher a flame from a decoy by comparing to 2 values, because a flame will always give off the maximum value between the 2 sensors, while a decoy will only set off one of the sensors because it will be out of the range of the other. This is very simple and efficient design. It's also analog, so we get to sample these sensors very, very quickly. It also has a detection radius of up to 7 feet, so we can look very far down the course. And then next up, we have power distribution, and Eamon will be talking about that.
Thanks, Travis. So in order for our robot to navigate autonomously without any guidance, we need a power source that can provide enough power for a long period of time. That's why we chose 4 lithium-ion battery hooked up in series that should give us 14.8 volt and with maximum capacity of 25 milliamp. And our robot in a full charge, in a full load, uses about 1.6 amp, and that should give us about runtime of 1.5 hours. And to step down the voltage from 14.8 to the 12 and 5 and 3.3, we're using linear regulator, and we're going to use the 12 volt to power up the batteries, and the 5 volt to power the microchip, and the 3.3 for sensors. And along with that, moving to the motors, in our design, we're looking for speed. That's why we picked four motors, 12 volt, 12 volt brushed DC motor, and with a gear ratio of 30:1, and that should give us about 350 revolution per minute. And with that power, with a 4.3 inch wheel, we should have a maximum speed of 2 meter per second. And with that much power, we need precision. That's why we're using the encoder sensor feedback, which it's a 64 ticks per revolution Hall effect sensor. Report back to that will send the feedback back to the microchip, and from there we decide if the robot is driving straight or no. We can adjust the wheel accordingly. And with our encoder code, we can keep track of distance and accuracy of if it's driving straight or not. Moving back to Hadi to talk about the water distribution.
The water pump and the 100 milliliter water tank are both located under the chassis to maintain a low center of gravity and aid in weight distribution. This also keeps any water from spilling into the electronics components located above. The pump we decided to buy can self-prime and very powerful and capable, delivering 2 liters per minute, which allows the output to be split into multiple nozzles without losing pressure. The nozzles being used are surface mounted in the front of the robot and can disperse the water with enough force and extinguish the flame every time. A MOSFET switch and power supply was implemented in the main DCB board to power the pump and dispense the water. The nozzles we are using are high vapor with a wide output, so the flame has no chance against these nozzles paired with 100 milliliter fodder. And now I will hand it to Jaron.
Our code consists of driving and sensor functions. The driving function is composed of many functions that allow our robot to have mobility, such as drive straight, turn, brake, and stop. First, we implement the drive straight function, which takes in 3 input arguments, which is the chosen motor, the direction, the speed. Within the drive straight function, it calls the encoder function, and it reads each encoder data, which is actually the actual speed. The actual speed is actually compared to the desired speed. If it does not match desired speed, the motor speed will be adjusted. Else, if all of the desired speed is matched, then we can call a motor function and give it the desired speed. We implement the drive straight function following the block diagram, PID controller diagram. And we also have sensor functions such as being able to sweep and detect flame or decoy. The way we do this is by collecting ADC values and then average them, because sensors have sensitivity error, nonlinearity over a long range of sensors, and dynamic error. And next, our robot will be using the wall following algorithm to navigate through a given course. And the robot basically hugs the right or left wall, whichever wall we choose to implement. And when it's hugging the wall, it adjusts the motor to the left or right, so it's parallel to the wall until it finds the decoy or flame. And here is a diagram of how a robot will function through the software. As you can see at the start, we turn on the robot and it turns on all the sensors. And the robot will go through the hallway scanning for decoy or the flame. And if the candle or decoy is found, then we can either implement one of the 2 following loops. If the candle is found, then we can put it out the candle by using our water distribution system. Else, if it's a decoy, then we will ignore it and go through to the next room. And the same thing will happen over again. We will go around the room looking for the candle or decoy. If the candle is found, then we will put it out. Else, if it's a decoy, then we go to the next room, and the entire thing starts all over again. If the candle is found, then we'll put it out. Else, if it's a decoy, then we will ignore it and continue on. And here's Travis with the IC decisions.
All right, so I want to talk to you guys about some of the decision process about the decision process that we had during the development of our robot. And we're proud to say that almost every single aspect of our design has been developed by us in-house. That is to say that every single PCB that we designed, we did here at San Diego State University. We printed it on our own machines. We used no carrier boards. And the same thing goes for our code. We used that PIC32MZ microprocessor, and we coded that thing from the ground up. We used no pre-assembled libraries. We used no bootloaders. We programmed it from scratch at the register level. And one of the reasons we did that is, well, first and foremost, we're all students here, and we wanted to be able to learn all of these processes and do it from scratch. And in a more professional sense, I believe it's more attractive to investors when they know that we've designed everything ourselves without having to rely on some other engineer making something and then giving it to us for us to use. And then finally, it allows us to configure things the way that we want it because we know the exact limitations of our hardware and also their strengths. The only downside to this process is that it takes longer because since we have to do everything ourselves, design it from the ground up, we have to build that foundation first. One of the most reflective areas that we can see this in is in our code. It's basically divided up into 3 tiers, the lowest tier being driver code. That's the very low-level code that's setting up the microprocessor, driving the pins, doing all of that very low-level decision-making. And then we have an intermediate step where we assemble functions that do certain things, like we might have a function that tells the robot to drive straight. And then we have our highest level code, which is the code that makes decisions about the course. It's reading the sensors, it's reading where it is in the environment, and then making intelligent decisions about what it needs to do next. Then next up, we have Gio talking about our milestones.
Here's a chart of our most important milestones. Driving in a straight line followed by autonomous locomotion was crucial in order to find and then extinguish the flame. Our final testing milestones help us work out any issues that arose during this time in order for us to be successful on competition day. And now Hadi will talk about our budget breakdown.
This project had a strict budget of $800. As you all can see, the majority of our budget was spent on the hardware, motors being the most expensive part of all. The next largest expense, accounting for 25%, was spent on the sensors. The electronics hardware consists of the batteries as well as the Solonius passive components. The IC packages and microcontroller only accounted for 13% of our budget. We ended up using $750 of our entire budget to build the best robot that we can design. There is only a small amount left of our budget left for any last-minute issues. Thanks for the team for being able to sample parts. This helps us to stay within budget. And now I will hand it to Gio.
There is also a final battle where each robot will compete at the same time to find and extinguish the candle first. You can watch this competition streamed online tomorrow at 1 p.m. Ask us how after the presentation for further details. With the hard work put in by the entire team, we have made a very unique robot and learned a lot in the process. We would like to thank San Diego State for sponsoring us and making this possible, as well as Big Frog for our team attire. Thank you very much.